Uh, First, I want to let you know that we have a guest lecture about optical lens. So that my old friend, Professor Weibo, Pia Watanabe, have been working on optical lens for more than 20 years. So that he's one of the leading expert in optical lens and is a member of SPIE, this kind of fellow. SPIE fellow is one of SPIE is very important this kind of international this kind of society, and he also chaired this kind of the conference in this area, so that and of course he is also very active in many international this kind of organization, including the things so that and you were surprised he's also now was selected by this kind of World Economic Forum to be one of 40 top scientists. It's pretty interesting to see that he got so many this kind of international this kind of recognition, including he also he was actually involved in this kind of one of Fraunhofer. Fraunhofer Institute is one of leading research institution in Germany. Okay, so there's two types of research institute in Germany. One is the Fraunhofer. It's really like the industrial research institute, like in Taiwan, E3, Hong Kong, S3. So that, and then of course, Germany has another kind of research institute, it's Max Planck Institute for Basic Research. Anyway, I told you he also was also not only in Germany but also in UK, and also so actually is something at least he have been quite active internationally in this kind of professional society. Okay, so at least I tell you that of course optical lens is not only for his talk. I also asked him to give some brief introduction about optical lens, micro mirror, so that it has been used in MEMS LiDAR. Right, MEMS LiDAR is one of important this kind of sensor for self-driving car, for also for this kind of HoloLens. If you look at what's happened, if you look at those Microsoft HoloLens 2, actually they also have ST Microelectronics, this kind of optical mirror for this kind of miniaturized, this kind of 3D display technology in VR, AR, MR systems. So that from my point of view, optical lens is one of important this kind of product. So that in the near future. So of course, I have some additional lecture about this kind of lens, and then so that I also want to still work on this kind of CMOS lens micro mirror using semiconductor process, TSMC, UMC, and Global Foundry and Kansas Foundry in Guangzhou. So that I told you there's something from my point of view. Actually, I do get some requests from the company in Shenzhen, so that this is one of key critical component. If US ban this kind of TI, digital micro mirror array chip, and then many companies in mainland China are going to collapse. I have guarantee. It's not only one company. Okay, at this moment, only one company in the United States, Texas Instruments, can make this kind of a digital micro array chip, so that the series of company, even public company in China, also private company make the all kind of product. They have to import from US this kind of United States, so that this is one of I would say quite critical component beyond those kind of advanced semiconductor chip beyond 10 nanometer. Okay, so that I will tell you that you think this kind of thing. This is of course that does give you some discussion. I think of course I may need to finish today's lecture right after this kind of 2:50, and then go to this kind of classroom to chair this guest lecture. Okay, and of course I do quickly look at your project, right? Some project, and then I know that at least two projects. One is related to this kind of Yunzhou text and mainship. Another related to this kind of this kind of main sensor with PID control. Okay, so that of course from point of view, and I need to give you some. I don't know if you have tried to study some lot more detail. Right? For example, if you look at those kind of a main chip, as I mentioned, so that in the beginning, I don't recommend you try to do very complicated this kind of modeling, right? Using computer, but at least you try to think about how can you try to use simplest way to do this kind of analysis. As I mentioned that, okay, and let me quickly give you some comment. So that so this is the project. I do believe this is actually I try to have some brief discussion with that senior marine engineer in this company, and then so that in general, as I mentioned before, right, so that you may need to think carefully, right, so that what's the for this kind of problem, what's the most important source of vibration, right? Most likely, as I mentioned, so that most likely it was most likely come from, I think, diesel engine. Engine, right? Engine is one of, I think we mentioned in our selected this kind of a chapter about this kind of vibration of engine, right? So that is unbalanced, and then you another thing probably here, and some additional transmission, gear train system, so that these are some one of I would say quite important source of vibration. At least you need to think about. This is I think I think here I think they try to use this US company's product, right? Diesel engine. And this is from United States. Okay, I just tell you thing, and then you, if you try to look at here, then basically you need to understand first is what's a typical, right? When we try we talk about all this kind of modeling simulation for almost for a long time now, so that you need to think about how can we come with a reasonable good way to estimate this kind of vibration based on simplified model, right? So that definitely the engine is one of a critical component. This is probably N2, and then this N3, and then so this is dominant, I would say, thing you need to think about, right? To think about how you try to create this kind of dominant this kind of thing. Of course, I think they give you that kind of drawing, engineering drawing, so that if you can use that kind of CAD software to think about how based on the design, maybe using SolidWorks, AutoCAD, so that can you try to determine based on the 3D model in the design, AutoCAD or something, and then estimate that the volume, and then of course if they give you some kind of material, I think they're using carbon fiber. That's another thing you miss. I mean, if you have a computer CAD program, right, and try to import that schematic drawing of this kind of a product, right, and then in this case, if I think now many of the CAD program, SolidWorks or AutoCAD, most likely, if you give them, I think they must have a function now, right, to estimate, for example, what's the typical volume of this 3D model, and then if you they give you some, I think they give you, this is the carbon fiber, it's a carbon fiber, right? It's another stainless steel material, and then so that you mean to think about try to get some of density, right? You have density, maybe low, and then you know the volume, probably from this kind of CAD software, right? Volume, and it is estimate the plus of the mass, right? So that that will be the one you can think about. Right? Of course, Yamaha, this kind of I think they also specify that particular engine model, so that you can try to go to the Yamaha, this kind of company website, and then download. They look at the specific kind of information to think about how you can try to. I know that for sure they have. This is I think pretty big company, right? If you try to look at their website, and then right, Yamaha, and then marine engine, I think they right, and that's specific model. I think the diesel engine. So that they'll give you, most likely give you this kind of specific, this kind of information about this kind of engine, and then so that in this case, this is something once they give you the model number, I think the four cylinder, right? Four cylinder engine, and then at least you can try to think about how to create this kind of at least estimate this kind of effective mass, and also spring constant. Then in this case, what do you think? How can you estimate spring constant? We'll talk about some different method now, right? For more realistic kind of three-dimensional structure, then how are we going to estimate this kind of spring constant? This is a practical thing. How are we going to do this kind of estimation about spring constant? It is overuse several method. I hope still remember. Right? What's the typical thing? First is we have n, right, from k, right, and k, and then of course you can use one thing is look at the solid mechanics, right? Basic k, maybe kij. So that based on mechanics, so that you can try to assume certain kind of structure, right? And then try to determine kij either two way. First is, for example, using the stiffness influence coefficient, or this, right? We have this thing, and also you may also, of course, there's another approach is if you're lazy, if they already have the CAP program, you may try to use this kind of software, FEM, try to do this kind of thing. Why do you think that's also possible? Because if they give you this kind of 3D CAD drawing, and you may also think about how to look at this kind of FEM method to determine this kind of spring constant. Actually, so that is something is important. Then next one, basically, if N and K, how about C? As I mentioned, damping is one of the most difficult part. So that either you can try to do vibration testing, or it can do make some assumption based on typical value from what I discussed in our lecture note, or some reference. So that this is a typical thing you need to do. So that is something. Damping is always the most difficult part for our vibration engineering associates modeling, but it's important for all of you to think about how you can get the reasonable, right? Reasonable kind of model to do this kind of thing. Okay. Of course, we already talked about this thing now in previous lectures, so that I do hope that at least you have some basic way to think about things. Okay. And for FEN, actually, I already mentioned in our lecture note, we do have separate lecture, right? We do have some additional. Maybe I should briefly mention about that concept of FEN based on this kind of engineering thing, so that FEN you can build the FEN model. That something is not challenging, right? FEN. We have a chapter about FEN. Unfortunately, we have limited time now. I can only briefly introduce about the concept, right? So that okay, and So this is something I give some advice for this particular group. Do you have any question? Huh? For this particular group, any question about the project? I didn't ask you to do very challenging, but at least you need to try to think about how to apply what we discussed, right? In our all the chapter, and then think about how to do realistic kind of a way on this kind of modeling simulation, determine what first natural frequency, vibration mode, right? And then think about force vibration. If there's certain kind of this kind of for engine, right? Engine the source, and then you can make some assumption. How are you going to solve this kind of more realistic issue? Actually, I do download that kind of the engineering. If you look at this kind of, let me quickly. If you look at this Yama, this kind of the website, and then they do provide some information about engine, marine engine vibration. So that they mention that typically in the low frequency range for engine, it's very difficult to overcome, okay, the vibration and noise, okay, so that that is one of the typical bar. And then also they demonstrate this Yamas, this kind of marine engine, diesel engine they have been continuing to improve their vibration engineering, so that the traditional vibration isolation rubber, you see, we are in this commercial the product, the diesel engine from United States. You see, our Yunzotech, they still buy this kind of a US product to this engine component to build their main ship. So that what's problem? Unfortunately, in mainland China, we still suffer about this kind of issue. Many engine or chip, right? Semiconductor chip is something we cannot do the good job. So that we still need to, even Yunzotech need to use buy this kind of Yama, this kind of engine, diesel engine to build their product. And you see, they really try to have a good engineering to minimize the vibration of the engine, vibration isolation rubber, and spatial constraint vibration system to reduce the vibration, right? So that anyway, so vibration is another thing is about creep, right? Creep, that means your viscoelastic damping, so that so they also show they can have a minimize this kind of problem. Creep is always issue for reliability of this kind of product, so that this particular engine made by Yamaha company in the United States, they really try to improve this kind of engine, right? So that that's something I just tell you that this company do spend time to make a good engine for Yunzotech thing, of course. And then of course I do know that they do have actually the company and they really try to have some additional more detailed engineering drawing. If you look at their engine, and then you can download a much more detailed technical information, right? So that this is something I just tell you. I think that this is something I think is one of a big company. They really make a good engine for marine engine, and that's something is important. Of course, another thing they actually I remember in terms of propeller, for the propeller, and then so that they do have some for the propeller part, so that according to the senior engineer of this company, Yunzotech, so that they bought the whole assembly, right? Propeller with additional this kind of gear train system and put in thing, right? So sometimes if you work on the product of this thing, so that most likely you do a system engineering, how you get all these components, and then you try to do this kind of integration. So that I just tell you that at least from my point of view is of course typically company is really they have to work on the real engineering, how they can do this kind of engineering design and this thing. So that I just tell you, this is something is some information for this student project. And any question for this group? And then, of course, another thing I know that the second group is working on that. Let me see. The second thing is related to the. Well, MEMS sensor have been widely used in what smartphone, smartwatch, mobile computing, and so that and even our DJIs and drones. So that in this case, for this particular project you propose, I expect you need to do a little more survey. What kind of thing you trying to solve, huh? For this group, so that what you're going to solve, huh? MEMS this sensor, your title is too general. Same things, design by PhD for what? So that I need to, at least from my point of view, you need to have some focus, right? Huh? You at least the title and the what I show here, you only have one reference. I don't know what kind of the thing you want to solve. Again, MEMS this kind of sensor, motion sensor, have been widely used in all kinds of products, right? And of course, another criticism I say, if you try to talk about piezoelectric accelerometer, most likely very few piezoelectric accelerometer they really use MEMS technology. I don't know. I really don't know about this group of students. What did you have any do some market research? A typical MEMS sensor we mentioned in our previous lecture. Do you see any product use piezoelectric to make accelerometer, like micro machine the accelerometer? Huh? This is an important thing. I need to give you some advice so that for this group of students, you need to polish even your goal. Huh? The goal can be much clear. What are you going to solve? And because this kind of a MEMS sensor has been used in a series of products with some kind of software control programming in MCU, so that if you don't try to do some additional market research and also this review, then you just get very generic this kind of idea. I will tell you that the final outcome of this project, result will be not good in terms of the current this kind of proposal. So that I need to let you understand about this important issue. Of course, if you try to focus on specific kind of unique MEMS motion sensor, this is another. MEMS gyroscope is has some product in the smartphone, but it's not using this kind of design, right? I also show you in one introduction about MEMS sensor, so that the traditional MEMS motion sensor smartphone most likely is capacity type. Okay, capacity is kind of a micro MEMS screen system, right? With the cone drive, so that this gyroscope definitely is what? It's a little bit better to have a high performance MEMS motion sensor, MEMS accelerometer gyroscope, so that I highly recommend, so that for this student group, if you want a good job, you need to spend enough time to study and maybe consult with my postdoctor. Right, my postdoctor, who Dr. Huang, right, Luo Huang, had graduated this summer, and then so that he worked on the microthermal gyroscope. Of course, he also has experience to use commercial MEMS gyroscope and commercial MEMS IMU, right, when he did his PhD research. So that I need to make sure that you need to spend enough time and effort to make sure refine your scope. Okay, so that and then try to make sure that have some think about what kind of problem, critical engineering problem you want to solve. Otherwise, this thing is still the writing is still not good enough. Okay. Again, any question for this particular group of students?
Or you mean you need to find a project?
Your title and your thing is very general. You didn't focus on some more. You need to spend enough time to think about, okay, what we're going to solve. Right? This is of course this is not paid research, but at least you need to focus on some specific this kind of engineering work, right? So that the choice is not something is clear. You just try to do this kind of design of reality control system based on MEMS, and it's so general. So general, the first thing. I don't know what we're going to solve.
So you just want to control the disturbance from the outside environment.
Then you need to make clear. Even the title, you think you need to for typical thing, then you need to make clear about what kind of real problem you want to solve using this kind of active control system, right? With sensor. And what having done, I believe you can find the real product on the market. In this case, it is sure. Not only this reference, even product. This is something you cannot ignore. This we spend the time just show one reference that's in the paper, and this one is not relevant to what you should talk. But here you talk about piezoelectric accelerometer, but the reference shows gyroscope. It's contradictory. This reference is not relevant to what you present in the page 1. I told you, just simply seeing I found some contradictory writing. Your reference is not consistent with what you want to do. Your piezoelectric accelerometer, you think what kind of MEMS you try to use, right, into the product for this kind of a design. Don't just write this kind of thing. It's clear. You don't spend enough time. That's something I can easily tell. If you look at my lecture note, okay, maybe I should quickly show the chapter 10, so that then I show you piezoelectric accelerometer is one of a very mature, but it's not a micro machine sensor, motion sensor. Most likely is a traditional piezo accelerometer using traditional fabrication process. So that I really don't know what your writing has really show something very contradictory to and that's something. Okay, anyway, now let me quickly show this kind of vibration this chapter.
This is what federal safety officials want to avoid. And new technology could help. Got behind the wheel at the Insurance Institute for Highway Safety, seeing how collision avoidance systems work. This car automatically brakes when it comes too close.
Yeah, this is the kind of sensor, motion sensor, micro machine. For instance, try to use an automotive for some kind of increased safety.
Cameras installed in the vehicle can detect more than just
a lot more sensor.
Faster speed. Watch what happens.
But not too hard. That would just fell over. Then the higher speed, we wouldn't avoid the crash. And there would be a crash, but because of the braking, the crash would be at a lower speed than it would be without the system.
The National Transportation Safety Board Wednesday added collision avoidance technology to its list of most wanted safety improvements. It wants states to mandate these systems, now available in luxury cars, in all cars.
We know that hundreds of lives can be saved and hundreds of thousands of injuries can be prevented. If the technology improves, you can avoid run off the road, rear end, and also the side departure opening of the collisions.
Other safety systems on the market include blind spot indicators, directional headlights, and an alert when a driver.
But anyway, I just here that show you that let me quickly show you this kind of thing. Basically, vibration testing and measurement is one of important part. So that I have limited time, so that we at least try to quickly go through this particular part, so that it will be related to the project you are doing, right? So that typically, as I mentioned, when we look at vibration engineering with two approaches, one is how can we do this kind of modeling simulation, another thing is what? How to do the vibration testing, especially in this MCK model. Our damping is one of most difficult. It's very difficult to predict from any kind of theory or software. So that most likely you need to do vibration testing measurement, right? So that in this case, vibration measurement has a way. First is look at our CPM, maintenance, right, of our machine. Maybe potential failure, to minimize this kind of loss of product, right, or danger, right? You can say. And then, of course, another measurement can be also used. How can you identify some optimize the speed of operation speed or RPM to minimize resonance? And I will make sure in the first chapter, we mentioned about a series of examples, like a helicopter, ground resonance, and so there's many examples to show this kind of issue. Right? And of course, with another thing is real migration measurement. Sometimes the result will be also different compared with those theoretical prediction from your model. So that and then next one is if you want to design active vibration control system, vibration isolation system, sometimes you may still need to using vibration testing to determine this open loop result, right? In terms of the passive MCK model, and then can you try to categorize this kind of you have a force input, and then your output x displacement or velocity and thing, and then once here, and then we shall think about how to use the additional sensor for active vibration control system, right? And then of course another thing, we can also identify some of MCK from system, and then of course we can also try to think, can we come with simplified model, right? So these are quite important technique. And of course, one final thing is the CPM, condition-based maintenance. So that if you go for the industry in Hong Kong, condition-based maintenance, you try to do some building service industry, so CPM, right? Condition-based maintenance, right? Of those kind of of certain kind of machine, right? In building service industry, it become one of a typical important thing. And I think even in some of the big machine like NTR, about 2 weeks ago, was a major failure of one NTR chain. So that I said Sunday, 2 2 weeks ago, right? During the weekend. So that that's thing, everything you move, and then after a certain long time, you may have some problem, vibration, wearing problem, and CPM is definitely another important this kind of important technician job. Technician job means you are not design a new machine, new product, but it's important. Why for all the existing product, we need to some company to hire engineer to do this kind of maintenance, right? So that that is something important thing. Of course, now we also have, I mentioned, we have what? It's a lot more sensor. Can we have AI-based maintenance, right? So that's something. Okay, so as I mentioned, like we do have some company in Science Park try to using AI for this kind of building HVAC in our commercial building, and Kano Innovation, right? It's a company in Science Park. They do a very good job in the COVID-19 period, and then try to help a lot of even casino in Macau and several building, commercial building in Hong Kong, Macau, to reduce the cost of this kind of building engineering right? So that's something, of course, now, as I mentioned, that why we like all the government try to think about how to use AI-based, AI-based this kind of maintenance. What to say? Predictive maintenance. This is something become important, and it's not for research, right? So that show you that we do have company in Hong Kong, in Hong Kong, like Kano Innovation. They really had a good team and get the funding from VC to make the real safe energy. So this is not for basic research, as I mentioned. So that let me quickly show you this company. It's a Kano Innovation. So that I happen know the one of the co-founder and CEO, right? So Kano Innovation is a company has exists for about, I think it's about 4 years. So that AI for building surface energy, to save energy and then reduce the cost, right? So that again is something. Now, once you have a lot more sensor, how can you use AI-based this kind of building engineering? So that's something I just tell you. This is something quite important, but somehow it's I at least in the lecture note I at least tell you there's some additional thing. Okay, quickly. So some students, like you students, say, oh, I get the sensor, I try to plug in and then plug and play, I get the data. Oh, what's the problem? Unfortunately, it's not that straightforward. Some of this vibration measurement or testing, you need to consider a lot more detail about how to get reliable data from your sensor, from your vibration instrument. It's something is not plug and play. So that anyway, so that let me show you some important things. Typically, the key concern for vibration measurement testing is first is that you need to have some rough idea about what's the typical range, the frequency for your machine, your engine, your building, or your main ship, or your DJI Joe. So you need to have some rough idea about what's typical the frequency, operation frequency and amplitude, right? Expected or estimate, right? That's why if you can try to quickly use what we describe in the 1 degree freedom model, right? To quickly estimate, what's the typical frequency of your product, right? And size the machine and structure involved, and condition operation a machine, and type of data processing. Oh, that's another thing. As I mentioned, if you don't care about this some of critical issue, then those data you collect maybe become the garbage. That's something I have to give you some general warning, right? So something is not plug and play, unfortunately. So that I do know our at least 1 or 2 project leader in Hong Kong CRC also asked me some of the issue about those sensors for their product design. So that this is something here I should quickly show you that in general, right? What's the typical way we can do this kind of vibration testing or model testing? Model testing is somehow it's the most sophisticated, right? That means vibration testing or model testing is that means most likely it consists with some shaker, sometimes electromechanical shaker, right? And that means you apply the voltage or electric signal and then generate some force, right? For time-dependent force to apply on mechanical system, and then you do some measurement about the motion, the response of this product. For example, you can measure acceleration, measure what? Displacement, velocity, and then using some of way maybe DAQ, data acquisition system, or FFT collect data and then mechanical this kind of measurement result will turn into voltage, and then try to do analysis about your result, right? And then try to evaluate this kind of time response or frequency response of this mechanical system, right? So this is a typical way to do things. Once you do the measurement, of course, if you have multiple sensors, and then if you're not only one sensor, multiple sensor here, and then the chance you can get the vibration mode. Okay, so that in this case, if you have multiple sensor in this kind of testing, and then possibly you can also determine a lot more information, right? So that this is something, and of course, as I mentioned, that the model testing, typically we try to focus on, for example, natural frequency, damping, vibration, or mode shape, right? And then, of course, during this kind of operation testing, in-service load, right? So that means sometimes your machine too big. You cannot apply this kind of loading without shaker. So that, for example, we have a building. I don't think you have way to put this kind of building on vibration table or some kind of shaker, so that those kind of a large mechanical structure like the building or bridge, how can you try to do the vibration testing? In this case, what you do? In service, that means in this case, in service load, that means we may try to, for example, for the building or bridge, how do vibration testing? What do you think? Sometimes one simple thing is okay. Maybe you try to leverage the natural disaster. If it big this kind of monsoon or typhoon, and then that is nature force, right? Not the man-made force applied on the building and bridge. And then if you have a sensor to measure the velocity of the wind, right? And then you can estimate maybe hydrodynamic jerk force, right? So that, and then you have additional motion sensor. In this case, you can also try to do this kind of vibration testing for large structure, tall building and bridge, right? So this is, I would say, in-service load for some critical this kind of a machine and product, it will be important. That's why in our Qingma Bridge, right? The long bridge near the Hong Kong airport, we have at least about 700 sensors, right? And Taipei 101 or the tallest building in the world in Dubai, then the all super tall building, most likely they have a lot more sensors, because in this case they don't have too much data, right, about super tall building. That they want to make sure that all the sensors can be used to monitor about health monitoring of a super tall building. Okay, and of course all the new car. So in United States, I think at least I was more than 5 years ago, U.S. government actually require every new car sold in United States, they have to install what? Black box for automotive industry. So that's something, so that you say in old day we have a black box for airplane once it crash, but it is a new kind of car. I think the black box, for automotive industry, it should become this kind of mandatory, at least for U.S. market. So that at least I think more than 5 years ago for sure. So this black box has a lot more this kind of low cost man motion sensor, right? And then with additional maybe some memory to record all this data. Once you have a crash, once you have a problem, and how are going to solve this kind of a problem. So this is something I tell you is important thing, right? And of course, when we look at how we try to measure to choose this kind of a transducer. Transducer has a more general term. What's a transducer? Transducer means actually sensor and actuator. I think we mentioned in our briefing them about this kind of means, right? So that so transducer actually a simple way actually transducer actually is mean there's a sensor and actuator. Okay, so that so in this case, when we try to consider how to choose proper our vibration sensor and actuator, so that the size of transducer important depends. Why? So of course, as mentioned, if you have micro machine or main sensor transducer, that would be much cheaper. Why? So that because we try to leverage the kind of semiconductor manufacturing process, right? So that the typical sensor in a smartphone, I told you, the price is around what? Around, I would say, less than $1. So that this is quite important for all of you to understand about why we have a lot more demand in the industry for this older main sensor, right? Because once you do the best packaging process in semiconductor process, like in 1 8-inch wafer, and then you can have no, I think not only 100, maybe 10,000 of sensors, so that in this case you can now really try to get the low cost this kind of sensor, right? And that is an important thing. And of course, I think we will mention, right? So they still have some traditional way to do some vibration measurement, for example, strain gauge. Strain gauge is still what they use. And so that in this case, if you mount the strain gauge, and then you, in this case, once you have this variable resistant transducer, right? Once the vibration, and then how you, this kind of strain you measure can relate to the vibration, right? Signal for this kind of mechanical system. And typical this kind of strain gauge, in old day, they're using this kind of metal, right? And then including, if you want to increase the performance, you have this kind of serpentine, this kind of very thin, tiny, this kind of wire, fine wire. In this case, it can increase the output signal, right? So that's typical thing. And then of course, there's another family, not only is metal, but using semiconductor. And in this case, semiconductor based, this kind of strain gauge, the output, right? Input output response will be much higher. So here I quickly show you the Whiston bridge, right? Strain gauge basically is a variable resistant sensor, so that in this case, you can see if we have this kind of strain gauge, so that apply the typical DC voltage, right? And then how we may measure this kind of output. This is our strain gauge output. This is the applied DC voltage, maybe from battery, and then so that once you have vibration, right, you can change resistance of this thing, and then in this case, it's clear we can easily analyze, right? If this kind of a change of resistor, how this can relate to output voltage, right? And of course, if this one is somehow we assume, the ratio of this resistance in this Whiston bridge has certain ratio, and then actually we can make of course assume some kind of gauge factor, and then our this kind of output voltage can be easily simplified now in this way. So this is typical thing, like has been used for, I would say, how long? I guess almost for 100 years. I try to mention one of a company I met about 10 years ago. I think this company is doing a very good job in this kind of using the strain gauge for real product engineering in large mechanical structure in the bridge or thing. I remember that the CEO and founder of this company, they actually come to Hong Kong to attend a conference, so that at least I think this company now become public company. They are doing a good product for this kind of vibration engineering thing, so that the CEO have been working on this. You can see now this become public company. Okay, it's more 10 years ago. The CEO come to Hong Kong to attend a conference, so that I try to emphasize that what I show you is something. Of course, you can look at this company's product. So they get not only this. I just show you the very basic thing, right? For all these things, so that you see they really make this kind of real time testing, right, of mechanical structure, right? So that and structural health monitoring, right, and structural dynamics. So that these are quite important things. I think they also got some project with like military, this kind of industry in military in China. So that that's why you can see now this become a public company. So that I surprised, but I know this CEO have been working in the industry for at least more than 30 years. So that yeah, and then of course now I show you piezoelectric transducer, huh? And this is typically in industry, B&K, this is Denmark company, is one of leading company make traditional. Again, this is traditional, traditional this kind of motion sensor for vibration engineering, I have traditional this kind of sensor, right? Motion sensor, okay, to measure the kind of acceleration, right? Acceleration, okay. So that it, again, it's why it cannot. What's the problem to make a micro machine, the accelerometer, using piezoelectric? What's the problem? Why your smartphone don't use piezoelectric? Motion sensor. Why? What's the problem? You still remember we have one chapter giving you a brief introduction about MEMS technology. So what's the problem? What's the problem? Then that's why I challenge you, the group of students you work on the project. It's clear that you really forgot about what discussed in our previous chapter. If you go through our chapter, we mention our MEMS technology, and we show you this kind of the video introduction of MEMS, then you will not make big obvious mistake. Micro machine, this kind of sensor, most likely if you use semiconductor, silicon based, silicon is what? It's not a piezoelectric material. So you cannot, it's difficult to make a micro machine is kind of accelerometer using piezoelectric phenomena, unless you deposit additional material. Right? If you use deposit some additional new material, then you'll be not CMOS compatible, and the code will be much more expensive. At least for smartphone, requirement low cost, until the $1 or below. So piezoelectric design of accelerometer is difficult to enter the smartphone business. Okay, so that is something I really don't understand about this group of students. Definitely you forgot about what we mentioned in our previous lecture. Okay, and okay, anyways, but still this kind of product still used in vibration engineering. Because why this is still used? Because this is quite expensive. But the good thing here is what? When you buy this kind of a sensor from this expensive one, they give you calibration certificate. Sometimes for those vibration engineering, for expensive vibration engineering for the product, it's quite expensive. The whole project, the building and the automotive industry is so expensive, right? So that they still can afford to buy expensive this kind of transducer, because the cost, when I was student, I would say about $1,000 to $2,000. Okay, compared with typical those sensor in a smartphone. So that it's expensive, but still it can be used in vibration engineering. So that anyway, I just told you, although it's still kind of expensive, but it has more reliable way for vibration engineering. And again, so here let's give you very simple way to describe about how. So basically, is that you have tiny proof mass, right? Mass spring system, and then you have some kind of a piezoelectric transducer. So once you have a vibration, right, and this kind of creates some force, and then in this way it generates some charge, piezoelectric charge, and then so that in this case we can mechanical input generate some charge, and then we have some transducer to convert charge into voltage. So this is the typical way we can make this thing. So here I show you very quick estimation. For example, if a quartz is piezoelectric material, we mentioned every smartphone, computer, or thing you will have this kind of a quartz oscillator, right, in your computer, smartphone, and all the electronic digital product. So that in this case, you see, we can quickly estimate, right? So that if you have certain kind of pressure apply, the mass apply on the piezoelectric material, and then actually we can estimate this kind of effective output voltage based on this kind of sensitivity of piezoelectric transducer. Okay, so that you see, so this will give you some very rough estimation about how we can estimate the kind of input-output response of the piezoelectric transducer using quartz. And of course, in terms of actuator, right, we need to try to apply some voltage or some force on our mechanical system for vibration testing. So that one of a very common way is electrodynamic transducer. Basically, it's a coil, right? And then with this kind of magnet, permanent magnet. So if you apply this kind of voltage and has some current through, in this case, what? Your electromagnetic, this kind of thing, and interweave with the permanent magnet. So that in this case, we have generate this kind of force, right, as exciter. On the other way, you can also try to look at this as a transducer as a sensor, right? If you have a vibration, and then this vibration can what? Vibration here can maybe velocity can relate to induce some voltage, right? So that in this case, electrodynamic transducer can be used for both sensor and actuator. Okay, one of my peer students, Hardy, actually have been make a micro machine of CMOS compatible. This kind of coil, micro coil, magnetic sensor, that be using for energy. How can we look at low cost, this kind of micro magnetic sensor to measure the power consumption of computer electronic system and things, so that at least I told you I have a student work on this kind of micro such coil magnetic sensor. If you look at my PhD student paper, while using the CMOS or CMOS main process in like 0.18 micron, so that at least I told you I have a PhD student do a very good job on this kind of thing, right? So that in this case, this can be used for what? Power energy, right? Energy monitoring. Right? We look at smart building. How can we make a low cost this kind of sensor using silicon process to design and make this kind of good, this kind of sensor to energy monitoring, right? For IoT, for smart building. So that's something I do have a very good peer student have done an excellent job, so that we can really try to make a good this kind of very compact, good this kind of micro coil magnetic sensor. It's so sensitive, and then if you look at our new paper, you can sense if you try to measure the power consumption of computer. Wow, you can really try to see if you use different computer program, and they can identify not only the energy or power consumption, but also try to understand all the software you try to use in your computer. So that if you try to look at Google, and then I do have a good research paper come with my student Hardy, and then so that he is he's a TA for this course that I think I told you. So that if you look at his work, and then I told you it's interesting to try to think about this kind of CMOS magnetic sensor. You try to think. My PhD student have done excellent job in this thing. Okay, so we have some good research paper just published with Hardy, our TA here, so that at least you look at the work done by Hardy, and then from our my PhD student and TA, and then I told you it really takes time, at least 1 year, 2 years, 3 years. Gradually, we can do some much better job compared to traditional this kind of sensor. So it's not something you can do in 1 month, 2 months, or 6 months. Okay, but once you make it, then it has a real potential impact in the industry, especially now we have a global energy crisis. How we have a low cost, this kind of CMOS compatible sensor to look at the smart building, smart construction to save energy. So this is, and of course, as I mentioned, there's a series of this kind of transducer, right? Accelerometer, they use piezoelectric tie, like a B&K company, and piezoresistor tie or capacitive tie. Your smartphone is using capacitive tie because this can be easily manufactured using like a semiconductor process like TSMC, CMOS process, UMC, GlobalFoundries, and SMIC in Shanghai. So that this is again, I emphasize this is the one now we can really make MEMS motion sensor. Okay, I hope that our one student group can really understand the difference, so that this again, this moment, very few, it's difficult. It's only conventional sensor. And typically, again, typical accelerometer is still it's a MCK system, right? So that itself it have an internal resonance, right? So that if you want to do a good vibration testing, you need to understand more. So this is a typical field response. Okay, field response of this kind of traditional piezoelectric accelerometer. Okay, so that so in general, they can of course they have a quite flat frequency range, right? And then so that there's still a mass spring system, right? So that so this is something important for all of you to understand a typical response. And then of course you see that's why all the sensor is not plug and play. How are you going to attach your sensor or accelerometer on the machine and product to get reliable data is non-trivial. So here I show you, right? If you just simply use maybe beeswax, and then the result here, if you have a much more of adhesion of this kind of sensor mark on your mechanical structure, right? And then so if you use some stop mark here, so that the result actually will be different. So that definitely in order to increase this kind of more wider frequency response for get the good reliable sensor data, so that you may, this is the best design, but it may be more expensive and then can cause some little trouble for your mechanical system. So they actually, so this give you some idea, right? This kind of how you can do this kind of mounting or installation of your sensor accelerometer may also cause some of the limitation of the frequency response, the range. Okay, and of course we also have a magnetic hydrodynamic sensor, laser vibrometer. This is the non-contact sensor, right? For example, one of quite expensive this kind of laser vibrometer has been used is a Polytech, the company in Germany, the 3D laser scanning vibrometer, and this is something expensive, right? Of course, I'll show you. Now your typical iPhone, new iPhone, you have a laser, semiconductor laser, so that like my iPhone 10 has a 300 laser. You cannot believe, huh? Not all the new iPhone, iPhone 10 has a 300 laser. Can you believe? But the solid state laser, using semiconductor process, now in a smartphone and for facial recognition, is that so that the 300 very tiny laser array, so that and then so that of course this is quite different, it's very large, this kind of machine to vibration testing, and then those kinds of solid state laser using in semiconductor process. It can be now it's used in the industry. Of course, in the near future, of course, we have also have this kind of using solid state, this kind of LiDAR, right? So that all this become a thing, right? So that in near future we'll have what? Silicon photonic technology, right? How you silicon not only make CPU, our CMOS sensor, silicon photonics. Can we think about using this kind of new semiconductor to make this kind of a series of this kind of sensor, and even this kind of a LiDAR, and also plus additional spectral photometer, like Apple actually really make this kind of silicon photonic sensor for Apple Watch, for mobile health. So that I told you there's a lot more new technology using optical thing. Okay, that's why this is something I need to let you know. I don't know, do you have any question? Of course, also have a LVDT, linear variable differential transformer. This is old traditional way, right, for vibration displacement measurement, and RVDT for this kind of the angular motion. Right? Of course, another angular motion you can using Hall effect sensor, or what my PhD student work on micro search core sensor using CMOS. And of course, they have additional optical sensor to make displacement like a photonic sensor. So there's a lonely thing, and then here LVDT actually is a very traditional one. And so the good thing here is you have very simple design using the this kind of a coil and apply the voltage. Once your vibration, then this kind of coil generates some voltage. The good thing here is it's not sensitive to temperature and high output, right? So that it's robust. And here I show you, of course, you can see a typical different sensor, different transducer, different operating range. So this can be important for you to consider. In general, piezoelectric accelerometer has much wider range, 20 kilohertz. Right? Loss transducer about kilohertz, eddy current more here kilohertz. Right? So that different type of design of this kind of sensor transducer, that they have different kind of frequency range. Okay, and again, the important thing is when you try to pick out the sensor or vibration testing, so it's important you need to consider about what kind of frequency range, right? How big your sensor and how big is your machine you want to do measurement. And of course, there's another thing as I mentioned, so that if you have your mechanical system is not too huge, then you have additional mass loading effect, so that your sensor or transducer can cause some change your mechanical system. Why if original M1, okay, MCK, and add additional this kind of sensor, right? A transducer, and then this additional this kind of additional mass, right? So this can change your overall frequent response or your whole measurement result. So this can be important issue. That's why you see So that in general, the guideline here, this kind of sensor, right? The mass should be about 1/10 of your product material system you want to measure to minimize the kind of mass loading effect. And anyway, so that there's a typical range, right? Once you select certain kind of accelerometer or the other sensor, so you have to look in the data sheet, look at their frequency range, right, which can be applied to useful for your vibration testing. Yeah. Anyway, so there's a trade-off. What do you say? The trade-off between a different type of sensors sensitivity frequency range, so that this is also quite important. And finally, there's another thing. How are going to mount the location of accelerometer? Why? It's an important thing, so that you have a big machine, then are you going to if you measure vibration, then it's important you need to pick out the right location so that your sensor signal will get highest one. So this is something quite important. Now next one is now I give you another quick overview about vibration measurement. Next, another topic is what? Model testing. I mentioned is sometimes some engineer in the company, they don't have enough time to do very sophisticated modeling. And then can we use the kind of quick way vibration measurement to the model testing? Why? So that the model testing, in this case, we have a more sophisticated way. Why? Still, we have some exciter, apply, and load cell, measure the force input and motion sensor response, input force measure and output response, and then signal conditioning signal, and then do signal analyzer and do some model analysis. So here, this is typical electromagnetic shaker, B&K company. There's a small and big one, right? And then, so that this is something you need also look at those kinds of frequency response for your shaker. And then, so that typically, okay, there are different type of shaker exciter. So different have different application. And of course, for B&Ks, this kind of piezoelectric accelerometer, typically they use this kind of charge amplifier. So charge amplifier basically is one special kind of electronic circuit tool, a particular design for piezoelectric accelerometer. Okay, so that and to minimize the problem, right? It's not a voltage amplifier. So here I show you the difference: charge amplifier and voltage amplifier. What's the difference? Charge amplifier. Why the B&K company they use charge amplifier? Huh? Because I think this is just typical electronic. Actually, charge amplifier is just like if you have a high voltage amplifier, and this is C feedback. Feedback this kind of capacitor, and then you have grounded. You have a very high gain voltage amplifier and a feedback capacitor. In this case, your measurement, right? So you have some piezoelectric thing from your sensor, and then in this case, this is grounded. In this case, with this kind of charge amplifier, the base structure. So this part, what happened to here? If this gain of amplifier, voltage amplifier is very large, and then this is virtually grounded, huh? Because virtually grounded. So in this case, we can minimize this kind of noise. So this is one of a quite important thing. Why this big B&K company, they don't use traditional voltage amplifier. They use piezoelectric charge amplifier. Can minimize the noise and minimize parasitic RNC. That means get more reliable measurement result. Right? So that's the reason why they use this. And of course, another thing, analyzer. Traditionally, we use this kind of, for example, HP dynamic signal analyzer, right? And then like 30, 40 years ago, we don't have powerful computer, PC, so that we have standalone this kind of analyzer, right? Basically, it's try to do the kind of FFT. Of course, nowadays we have a so powerful computer, your Mac can do all this FFT, and your smartphone app, right? I show you in the beginning, and as you do the first homework, so that all the this kind of smartphone has very powerful processor, right? So that all the FFT becomes so easy now. Basically, once you have FFT or fluid transfer, basically is once you take time data, time dependent motion sensor data, and then convert into frequency domain. And then in this case, we can really try to now look at frequency response function, right? So key here is I think I skipped the part anyway, so that the once you have do this kind of measurement of sensor data, and then do FFT, right? Either computer or something, using all these things. Again, before we get the more reliable data, there's another thing. All these kind of our sensor need to what? Or digitize into computer, or digitize into your smartphone, or digitize into your MCU, microcontroller unit. In this case, there's some kind of finite sampling rate. So that in this case, if you don't carefully choose right the sampling frequency, and then you have some aliasing effect, that means you get the fake data, fake, not reliable result from your thing. That means that in this case, we may need to add additional anti-alias filter. In simple way, basically it's low pass filter to filter high frequency noise when you do vibration testing. That's why I told you these are some new things. So here I say, Chris, when we do this kind of sampling, right, using ADC in your MCU, well, some data acquisition system connect to your computer, right? In this case, once you do the sampling, and actually you can introduce this kind of multiple, this kind of thing. Original thing is not here, but once you sampling, you have a multiple, this kind of frequency, this kind of component here, and then this can create some problem. Okay, that's why in this case, what we see, then what we need to think about how to do this kind of a low pass filtering and aliasing effect. This is something important. In this case, we do the low pass filter, right, to minimize this kind of problem. Okay, so that the alias phenomenon here, so that that is something quite important. You see, if you have right sampling, and then you have quite reliable result in measurement, and then you have a wrong sampling, you have some fake result in your measurement. So this is something quite important. I think we almost run out of time, so that unfortunately I think I have to give this kind of thing, right? So that one final thing is spatial leakage. When you try to do the measurement from the sensor, that's another small issue. Spatial leakage problem. Can you? So that's why it's sensor is not plug and play. So that the leakage, that means in the frequency domain, so that it produces an actual frequency which is not something the real one. So you may use a window effect, try to do additional digital signal processing to make sure that minimize the problem. Anyway, so that so today I just quickly give you some very brief introduction about vibration measurement. So that for sure, this part I would say is quite important, right? It's part of I would say we talk about this kind of modeling simulation, 1D feeder, 2D undefeated, and this kind of modeling MCK, and then vibration testing, and then so that this is a complementary to our this kind of vibration engineering. So that finally I just show you that typical we use this kind of frequency response function to do vibration testing. So this is a typical machine, right? Like spatial analyzer, FFT analyzer. Actually, our department do have this kind of a very old, more than 30 years old now the kind of FT for vibration measurement, so that although it's old, but still it's quite reliable for vibration testing, so that it's maybe older than over you. I think this machine is more than 30 years old, but still quite reliable. Okay, it's still and so that we still use this one in our research. Okay, so that's something I should tell you. Although it's old, but still this is the instrument, right? Still it's useful. Okay, I think we probably finished this one. Do you have any question? Huh? If you of course you have no more question, and then so that welcome, you can try to this kind of obtain this guest lecture now in from this Professor Weibo, and then so that again, if you have time, and you're welcome to attend this kind of guest lectures at 3 o'clock, so that that's something for sure. At least you learn something a little more, right, on this kind of thing. This kind of micrometer is another one, torsional MCK system in micro scale to make this kind of a product for this kind of confocal micro endoscope, right, for cancer diagnosis. Okay, I think that's it for today's lecture. Okay, I think if any question, please try to ask